Okay. Part of the reason why I like this one too is it actually gives me an example of a real problem that I would have. Where would I use these things? So what I said here is that I'm measuring a current. So if I were to build, if this were a real thing, what I would have is a device here called a CT, and that CT would look like a donut, and you'd run a wire through the donut, right? And what that would give me is some current coming out that would be related to um, so it would be it's a current transformer. Basically, what it is it's going to give me a current here, which would be 1/2000 times IAC going through this thing. So I can model that thing as a current source. But this would be so. If I had a control system, I had a microcontroller, I want to have this microcontroller controlling something, I would have to get that if it's trying. So if I use the example of a PV system, a solar system, basically, if I'm using this, I need to control that current. I want that current to look a particular way. If I make a PV inverter, it is trying to be a current source. And so I'm trying to make the current look like whatever that is. So to do that, I got to measure it. All right, so 20 cosine 2 pi 60t. So let's just basically what this is 3 op-amp circuits together. All right, there's the one in the box, and then there's the other two. So the way I approach this problem is I say, all right, this current coming out here would be AC, and it would be 1/2000 times this thing right here. So 1/2000 times that thing right there, that is the current that is flowing right here. All right. Now, what I want to have happen is I want to convert that signal into, by the time I get to V out, what I'm saying is I want that thing to go from being this. So what would be the peak value? So 20/2000, what is that? 1/100. So basically, this guy would be going 100 milliamps to minus 100 milliamps. Somehow, I want that to turn into that, where this is 5 volts and this is 0. Right? So what am I doing? Because a microcontroller, it's got what's called an analog to digital converter. So it takes this analog signal, which is continuous, and converts it to digital. And the analog to digital converter, you haven't learned that yet, but basically if you've used a microcontroller for anything, you might have. They have a voltage range, maybe on the order of 0 to 5 volts. So somehow I got to take that waveform that I have right there, that 100 milliamp thing, and get that into a voltage that goes from 0 volts to 5 volts. That's basically what this is what's called signal conditioning. If I'm doing an embedded system, I would have this type of thing to shift those kind of voltages around. Okay. All right. So, all right. The way I do this is I view this as basically 3 different circuits. So the circuit in the corner, right, for V1, let's actually separate it out for a second. Let's do the middle circuit here, the guy in the box. So R2, R3, R4, R5. Okay, so I called this like this. Okay, so what is it? R5, R4, R2, R3. Now, some of you might have looked this up online and already found the answer to this. All right. It's actually a pretty there's a whole slate of common circuits. So I call this V2. That's a node voltage. And I call this V1. That's a node voltage. All right. And this is V out. That's a node voltage. Okay. All right. Where do I start with this analysis? This is actually almost the exact same circuit as problem 1 on the practice exam. All right. It doesn't have any capacitors. But I could approach it the same. If you noticed in that particular circuit, the impedance here and the impedance here are the same. All right, we're going to go back to it a little bit later. But how do I start the analysis on this one? What's that? Golden rules. What are the golden rules? No current here and no current there. Yeah. I plus and I minus are 0.
The voltage of the 2 channels.
The voltage of those two terminals are the same. So basically V plus, we say, is equal to V minus. All right, now, how would you approach this?
Do a voltage divider at the bottom.
Do a voltage divider at the bottom to find V plus. Okay, so V plus is what? V2 times R5 over the series combination R4 plus R5. Like that. Okay. Do I follow that? Why a voltage divider?
Because it is one.
That's a good answer. What makes it one, Jacob? The current's the same. I got a series combination of resistors. That's a voltage divider, right? If I have a series combination of impedances like that. So okay, so V plus is that. So how do I use that? For the top portion, well, I got a whole bunch of different things I guess I could do. I also have a voltage divider up on the top as well. Although a weirder one, because I do have I guess, yeah, all right. I do and I don't. I do and I don't. I don't want to do it that way. Let's do it your way. So you want to do a KCL. Okay. So I'm gonna put words in your mouth. I'm gonna do my KCL this way. All right. So see, this was R2. Okay. So, all right, if I defined everything that way, help me out with the KCL. I do the KCL here. Okay. So how would I write that?
V1 minus V negative over R2.
V1 minus V minus over R2
equals V negative minus V out over
R3. And what is V negative?
same thing V plus.
Yeah, so I plug this in here and here, and boy, is that going to get ugly, right? Going to get ugly. Okay. All right. So, but turns out to be, let's say, for sake of argument, I don't know, how did I phrase the question? I don't remember how I phrased it, but if R2 equals R3, if they were all equal to each other, I think I phrased it that way. They were all equal to each other. So let's make them all the same value R. What happens if I do that? Well, so this guy becomes V1 minus V minus divided by R2. This becomes V minus minus V out over R3. Like that. Well, sorry. R. You guys with me there? If they're all equal to each other. It could be any number, 100K, 10K, whatever. Right? What about this V plus equal V2? What would that become? It would become V2. So see, it would be R over R plus R, right? Which would be what? R over 2R, 1/2, right? So it'd be V2 over 2. And that kind of makes sense, right? If these two voltages, if R4 and R5 are in series with each other, and each one is the same value, I should have half the voltage appearing across each one. Think about KVL, right? A voltage source that's 1 volt across a series combination of each resistor being the same, I'm gonna get half a volt across each one, right? All right. So V2 over 2. So basically this becomes, if I take this result here, plug it in here, we'll do it here. So V1 minus V plus over R equals V plus minus V out over R. V plus equals V minus equals V2 over 2. Plug that into here. V1 minus V2 over 2 over R equals V2 over 2 minus V out over R, like that. Now, if both sides end up being over R like that, what's that mean? The numerators are equal to each other, right? So the over R's disappear, right? And if I do this, I know how I would have done this. What I just did didn't come out to what I... Oh, I know why. That's why. All right. Yeah. Okay. No. I don't like what I just did. Um, All right. I'm gonna start this over because what I just did didn't give me the right answer. I've never done it that way before, but something it should have given me the right answer. I don't know why. What I'm actually gonna do is superposition. All right. Now I'm gonna do. It should work with nodal analysis. I'm gonna do superposition. I don't know what if I'm smoking something or what. Let's make this V2. Make this V1. All right. And I am all right. I'll keep it this way for now. So R4, it's really ugly when I keep them all. I'm gonna make them all R. All right. It makes it a lot less ugly when I do it that way. Yeah.
On two parts, so just making a differential.
What's a differential amplifier? That is that. I mean, yes, it is. An op amp's a differential amplifier itself, I guess. This guy, what I call this is a subtractor. Sometimes you get called a differential amplifier. But let's see what's going on here. If I do superposition for a second, right? And let's say I turned V2 off. Let's start there, right? So V2 off. So V2 is off. I make that 0. Okay. So the voltage I get right here, because this is probably how a lot of you guys did problem 1 on the practice game. I'll call that V out 1. Okay. How would I approach that? Golden rule tells me what? V plus and V minus are equal to each other, right? So usually what I do in my op-amp analysis is I look to say, well, which one of the two can I determine from looking at the circuit? So which one can I determine, V plus or V minus? V plus. What's V plus? 0. Why is it 0? Well, not necessarily because V2 is off, but basically because there's no current going through there because the op-amp doesn't have any current, right? If V2 was there, then there'd be some current going on over there on that side, I guess. But there's no, if given the way this is set up, there can't be any current going here, any current going here, because there's no current that comes out of the op-amp terminals. So there's no sources over there, it couldn't work. All right, so basically I get the V plus is equal to 0. So that means the V minus is equal to 0 as well, okay? Now I do a nodal analysis on this thing, and I call this 0, and I have V1 minus 0 over R has to equal 0 minus V out 1 over R, like that, okay? What does that lead me to? That leads me to the fact that V out 1 has to be equal to negative V1. Okay. You guys with me there? And what would it have been? It would have been the ratio of the resistors. If I kept them as R2 and R3, it would have been the ratio of those two resistors. All right. In fact, I'll just do that real quick. R2, R3, R4, and R5. R4 and R5. That would end up being here R2, R3, and this would be the ratio R3 over R2. Like that. Okay. Now, the other one's a little bit trickier, right? If I turn off V1 and turn on V2, let's do that one. All right, so I'll leave them this way. R2, I'm going to regret that here. All right, so if V1 is off, I short it to ground. And so this is, let's see, so R4, R5. That's V2, and that's R3. Okay. Now, this I would call V out 2 because it's the voltage coming from the V out or the V2 source. Okay. So what would I do here? What would I do in this situation? Any ideas? Yep, I do voltage division at V plus. Perfect. Yeah, so I'd say V plus is what? V2 times R5 over R4 plus R5. Like that, right? Now, what's that equal to? V minus, right? V plus and V minus have to be equal to each other. Now, we did a problem just like this back in lecture, right? What I also have is a voltage divider now, a clear voltage divider with the R3 and the R2, right? Whereas it's like the voltage source V out 2 is getting all that current from V out 2 is going this way, right? I get a series combination of those resistors, right? Right. So basically V out 2 times R2 over R2 plus R3. Just make it clear that that's R3 is equal to what? What's that equal to? Where's that voltage? That voltage divider relationship tells me I just wrote the voltage where? At V minus, right? V minus. So what do I have here? I put those two together and I have V out 2 equals, let's see. So V out 2 equals V minus times R2 plus R3 over R2. And then I plug in the V minus. So this becomes R5 over R4 plus R5 times R2 plus R3 all over R2 times V2. Okay. What did I do here? Right. So I plugged in V minus is this. I plugged that into here and got that whole thing. Ugly, ugly looking thing. Yes, sir.
Well, I don't see how do you get the V out to RO out to the
It's a voltage divider, right? What I'm saying is if this is a defined node voltage, right? The current, there's no current that comes out of this op amp. I guess that's the other. So basically, there is essentially a current. These guys are in series with each other. I can think of this as a voltage source, that the voltage source, actually, whether there's a current coming out of there or not, basically I have a defined voltage across R3 and R2 in series. And I know they're in series because there can't be any current leaving here. Right? So in other words, I'm doing a KVL and I'm going from ground through R2, through R3, into this voltage source to ground. Right? That's a situation where I know the voltage across the series combination, so it gives me this. Okay? So then I set those equal to each other. So what I end up with is that V out is equal to V out 1, the result from source 1, plus the result from source 2, right? Like that. So V out 1, what did we end up with for that? We ended up with minus V1 times R3 over R2. So minus R3 over R1 times V1. And then we ended up with this ugly looking thing here. This guy is plus R5 over, what is it? R5 over R4 plus R5 times R3 plus R2 over R2 times V2. Ugly looking thing, right? I think we can all agree that's not the prettiest expression in the world. What's true if R3, so this is, I think basically that's what I kind of asked you to get to, although I don't think I ever asked you to enter this anywhere. If I have this is R2 here. Okay. If all of those resistors, R2, R3, R4, R5, if they're all equal to each other, what happens to that expression? Yeah, so if R3 and R2 are equal to each other, that first term is going to become negative V1, right? That other term there is going to become what? Well, I'm going to have basically I'm going to have R over 2R and 2R over R. That would end up becoming V2. So in this case, this guy becomes V2 minus V1. So sometimes call it a differential amplifier. I usually call it a subtractor, right? What to do? It takes two voltages and subtracts them, right? And that's a common thing. If what I'm trying to do, like I said at the very beginning of the problem here, was if I want to shift something up, right? What I end up doing here is coming up with a way to shift it up. So sometimes we think of this guy with a picture where I draw the picture like this, where here is V2 and here is V1. And the result would be that. That's something called a block diagram. We deal with that in control systems a lot. But basically what I did was I built that block. I figured out a way to subtract two voltages from each other. All right. You guys with me on that one? This is pretty similar to problem 1 on the practice exam, which we'll get to. What about the other two blocks there? Or were those easier? Those should be easier, right? If I look at the first block up here in the corner, what's that do? What does that do? How do I analyze that one? Just one KCL. Whatever current goes in here has to go there, right? Now, what's the voltage what's the voltage relationship here? What's true about V plus and V minus? They're both 0, right? Why are they both 0? Again, when I look at this, one of the nodes is usually obvious to me. The one that should be obvious is this one. How much current goes through that resistor? None. That means that voltage is 0. So that makes V minus 0. So if V minus is 0, then looking at that top guy, I have, if this is the circuit, a resistor here, and a resistor here, and I have this current source here. If I do this with phasors, this was 1/2000 times 20. So this worked out to be 0.1. So I have 0.1 amps there. How do I figure out the voltage here, which works out to be V1? How do I work that out? Is it 0.01? You are correct. It's 0.01. Yeah, 0.01. Right? So if I look at this, what would V1 be? Well, let's check that out. So it's going this direction, right? So if this voltage here is 0, and do my KCL right, I basically see that I have 0.01 entering, and I have, in this case, 0 minus V1 over R1 there, right? So it actually works out to be that V1 is equal to negative R times 0.01. Okay. Now, what I said was I wanted the peak value of that, the amplitude of that. This voltage would be a sine wave, right? And I said I wanted its peak value to be 2.5 volts. So that meant that R1 here needed to be what? I don't know, 2.5 volts. So this is how you would do a design problem, right? You guys just do an analysis. How big is the voltage? When doing a design problem like this, it would be, all right, if I want that value to be 2.5 volts, what resistor do I get? Right? That's how you build a circuit. All right. So what would it be if I wanted 2.5? Who knows the answer? Yes, it would be 2.5. But so what would that be? Is it 250? Yeah, I guess that's right. So 250 times 0.01. So yeah, that'd be right. Yeah. 250 ohms. All right. So I said its peak value. Basically, if I think about this in terms of phasors, right? This basically what it's saying is that the voltage I have would be what? It would be 2.5 angle what? Because that the resistor is not going to be negative. When you solve this thing, you're not going to get to the resistor. Yeah, 180. If somebody says, well, I need a negative 250 ohm resistor, right? That doesn't exist. A 250 ohm resistor does. The negative sign means that the voltage has a phase shift as it goes through the circuit, right? That's what the negative sign means. All right, so it would be that. Okay. Questions about that? Yeah.
Did the current have like
It did. We were told that the current back in the beginning of the problem, that the current was this IAC. So that means that it would have been 20 angle 0. Right.
it had the angle you have to add that?
Yeah, you would. Yeah. That's right. Yeah. Basically what it tells me is if what what would that look like? If I looked at this on an oscilloscope, the actual value coming out of this would have been 0.01, not 100 milliamps here, but 10 milliamps. 0.0, so 10 milliamps and negative 10 milliamps. If I looked at an oscilloscope, what would the voltage V1 look like? Good question. What would it look like? According to this, it should be 2.5 angle 180 degrees. Okay. So this current here looks like this. So this guy is 0.01. This is I think it's about to try to close this on me. Yep. Sorry. Magical combination of strokes with the pen. what's it going to look like? If I have a 180-degree shift, what's it going to look like? If one of them is a cosine, what would the other one be? Be negative cosine, right? So when one's peaking, the other one would be at his minimum. Oh boy. Here we go. Good. Okay. All right. We're back. All right. So anyway, that's what would happen in that particular case, right? So this guy would go from this picture to a flip of that. All right. Let me not fight with it too much. Okay. All right. Now, what about the other circuit there? The other circuit was this guy. I had a 15-volt source, and then I had two resistors. Like that. Right? How much current goes this way? None. So what do I have? I have another voltage divider, right? V plus and V minus, what are they equal to here? The same thing, right? V plus and V minus are the same thing in this circuit, right? So which one can I tell? Yeah, so which one is R6 and which one's R7? All right. Okay. So what is V plus? Yeah, so this is 15. So this would become R6 over R6 plus R7 times 15 volts. Right? So what do I know about V? This is V2 in my circuit. What do I know about V2? V2 is equal to V minus, and V minus is always equal to V plus. So this is R6 over R6 plus R7. Like that. Okay. And what I said was, for my output, my total output of the whole thing is V out equals, for that circuit that we had, this differential amplifier thing, right? I had that V out, we found V out was V2 minus V1. Okay, V2 minus V1. What I asked you to do is do a design problem where I said, okay, well, I want V2 there to be 2.5 volts. So you choose the resistor to make that happen. So this basically becomes 2.5 volts minus V1. V1 was 2.5. This is where it gets tricky, right? This is a DC value. V2 is a DC value. What's V1? It's an AC value. So it's a little bit weird. So the way I think about this in my head is, what would this be? V1 is something that looks like that, right? So what it's going to look like is this, right? It's going to be a sine wave that's shifted up. It's a sine wave that has added to a 2.5 volts, so it's moving up. Okay. So again, 3 op-amp circuits. These op-amp circuits are, the last 2 we did should be pretty straightforward to you. The first one we did, the subtractor, probably less straightforward. All right, but it gets us to probably the harder problem for you, which is this guy. Now, I don't remember. I think what's going on there is you got a 500K here. And you had, I don't know, 1 nanofarad here. And then you got 100 kilo ohm here. And then this one's V2. Is that right? Which one do I call V2? I think so too. Let's call this V1. Let's call this V2. This is 100K, 500K, 1 nanofarad. Now, a couple of ways to approach this. I could do nodal analysis. A lot of you guys could superposition because I asked you for two different transfer functions. So that's probably what I would do is superposition. It's actually the exact same thing that we just did, right?
It's not always the case.
What?
We have two voltage sources that we use superposition. Is that
No. No, I mean, you can use nodal analysis just fine with this, right? I had some kind of brain fart on whatever I was doing before. I don't know what's going on. The nodal analysis should be totally fine with this. Yeah. Looking at this, if I try to, here's the way I look at simplifying this is the 100Ks are the same. I'm going to call those, in my mind, I call those R. Call this R, or maybe I'll call them R1. Okay. What do you notice about the other components there?
parallel?
Yeah, the 500K and 1 nanofarads in parallel in both cases. All right, so basically what I'm going to say is I got a Z up here and a Z down there, and Z is what I'm going to call R2 in parallel with 1 over S times C, right? That is that's what that impedance is. All right, now if I were to go through the math on that, so if I did the calculation, that would end up being R2 over SCR2 plus 1. All right, how do I know that? Well, how would I have done that? How did I get to that? I'm skipping the simplification because I know what the answer is. Yeah, so how would I have done it if it's a parallel combination?
The 1 over R2 plus SC, and you get a common denominator.
Yeah. So I do 1 over R2 plus SC. So 1 over the resistance plus 1 over the impedance of the capacitor, all raised to the -1 power. That would end up being this. Right? You should be able to see how to do that. What I then do is I look at this and I say, well, that means that this whole thing looks like, you could have kept it in terms of all those components, but it gets ugly, as I'm sure many of you know. This is R1. I'd call this Z. Because I can do that. I can replace those with a parallel combination like that. This becomes Z. And then I've got R1 here and V2 here. Like that. And that all leads to V out. Yeah. And then I basically just go through the same analysis that I did. Right? I would have done it the exact same way I just did it. Right? I'd do superposition. So where's the easiest one to start with? The easiest one to start with would be to turn off V2. Right? If I turn off V2, what's this turn into? Well, I could do a KCL. So I got Z. If I turn off R2, then I got this guy here goes to ground, right? Like looking at this, if I turned off V2 here, then I'd have that resistor to ground, and this guy was R1. They're the same value. Okay. So it's just that. What is V plus? Without me drawing anything else, what's V plus? 0. What's V minus? 0. Okay. So here's R1. Here's Z. And there we go. There you have it. This is V out 1. this would be V1. I would do a KCL at this node. All right. This is where you guys should be comfortable enough with circuit analysis to say, okay, I do a KCL at that node. I'm going to see that V out 1 is going to be equal to negative Z over R1 times V1. Right? I would get that for doing the KCL right there. Questions about that? I'm not going to do the KCL. All right. How would I approach the other one? First of all, so in terms of this being a transfer function, let's say, right? What's the transfer function for this?
It's D over, D over R.
Negative Z over R1. So that would become, given what I just wrote for Z here, being that, this would become negative R2 over R1 times 1 over SC R2 plus 1, right, times V1. So V out 1 over V1, if I wrote it this way, V out 1 over V1 is my H1 of S. And that is simply negative R2 over R1 times 1 over SC R2 plus 1. Now look at that. How many poles does this have and how many zeros does it have? 1 0 and 1 pole, right? 1 0. Well, sorry. Whoa, what am I saying? 1 pole, no zeros. 1 pole, no zeros. All right. What is the pole location for this thing? What's the pole location?
Negative 1 over C.
Yep, the pole location, I have S equal to negative 1 over CR2. All right. What's the break point? Yeah, 1 over CR2. All right. What's the K value here? K is equal to negative R2 over R5. Or sorry, R1. Thanks. What am I talking about? Negative R2 over R1. It's the multiplier in front of this whole thing. That has this in the standard form. K over S tau P plus 1. All right. That's how I do that mapping. Okay. You guys with me on that? Yeah.
R2
Is what?
R2 in the impedance value.
It is. Yeah, that's where it came from the impedance value.
So if we go in question of S, so like H1 of S would just mean like superposition, like the alpha.
Yeah, if you have this on a test, superposition would probably be the way to do it.
So like you just said H1, H2, and then it said the alpha. Or the alpha. So it had like 3 variables.
Yeah, so the other way, yeah, okay, good question. The other way I could do this is I could have not done superposition.
Yeah.
And I could have done nodal analysis. If I did nodal analysis, what I would end up with, and we could probably do it, I would end up with this: V out of S is equal to H1 of S. It would be some ratio times V1 of S plus H2 of S times V2 of S.
And then hold on, I didn't only get like those variables, so like kind of like so I did the EA. The 3 variables, the out, V1.
Well, what you would do if you try to do this by superposition, right? What you would end up with is you'd have to do nodal analysis at 2 nodes where you'd say this is V plus and this is V plus. And you'd have to do your nodal analysis and solve for V plus from one equation and plug it into the other one.
Yeah, I did that. And then, I just didn't know we could write like V1, V2,
But yeah, you can. I mean, if I did nodal analysis, I would totally end up that way. Yeah. Yeah, no, it's yeah. I mean, sometimes I think Yeah, sometimes I think you do know it, but you don't know that you know it. I think that's probably the, because if you didn't know anything about transfer functions, you would have just said there's two voltage sources and you would have done nodal analysis and you would have had something in terms of V1 and V2. Once you start knowing little bits and pieces of everything, it all gets more confusing. But if you think about it, too, superposition is a mathematical trick. When I work a circuit, I don't take V1 and V2 and turn them on and off independently to analyze it, right? They both work together. If you think about superposition, what do you do with a voltage source in superposition? Well, you turn it off, right? And you turn it on. When you turn it off, you set it equal to 0. So if I turned off V2, what happens to this term? It goes away, right? So I get it should square up with what I get. So it should end up looking like this fundamentally. It's whatever component I get for V out when V1 is on. And then if I do the opposite, then this guy, when I set him to 0, by turning V1 off, I get that result. So it turns out you get the same result either way, because you're really just doing a math trick when you do superposition. All right. Now, to get H2, you would do superposition, or again, you could do it from nodal analysis. And you would end up getting for that, I don't know. That's the ugly one. What I probably would do with that one is I would do it minus plus. I would say I would do that the same way I did that subtractor circuit, where this is Z, this is R1, this is V2. Sorry, this is Z. This is R1, and that's ground, right? This would be here, this voltage would be V out 2. Okay, how would I do that? Where do I start with that? We already did this problem.
What if each is 0?
No.
Your voltage divided upon.
I had a voltage divider. Yeah, so V plus and V minus are equal to each other. One of the nodes is always easy to figure out. In this case, the one that's easy to figure out, it's pinned by the input. When I say easy to figure out, somehow it's pinned by the input voltage. In this case, the input voltage V2 pins this guy, pins this node at a set value. So V plus has to be equal to Z over Z plus R1 times V2. That's equal to V minus. So what I would do now is just like I did previously, it looks like if I do a KVL around the loop that includes V out 2, Z, and R1, I have another voltage divider that says V minus equals R1 over R1 plus Z times V out 2. I'd plug this into here and solve. All right, what would that end up being? I think it would end up being Z over R1, right? I think if I put those together, I end up getting V out 2 is equal to Z over R1 times V2. Like that is what I would end up with. And then I plug in my Z, the transfer function I got for Z, the impedance, and that would end up being R2 over R1 times 1 over SC R2 plus 1 times V2. So I got another transfer function where in the standard form it's K times 1 over S tau plus 1. Okay. Questions about that?
Like, if I do the multiplier, does that mean like the EN is 2, the R is 4, like if R is 2, then
The multiplier is just this is the math thing. When I look at that transfer function, I got a constant, R2 over R1 is a constant, times 1 over S tau plus 1. So the constant on the whole thing is whatever the K value is. So in this case, R2 over R1 is 5, I think is what it works out to in this particular example. Now, I will say, I think I think I wrote an S squared. I think, if you look at the general form, I think I wrote it as K S squared times S tau Z plus 1 all over like S tau P1 plus 1 S tau P2 plus 1. All right, there is an issue there because there is no S squared, right? That doesn't make any sense for what I have here. I should not have had that. All right. If this is my standard form, then what do I know about K? K is R2 over R1. What's tau Z1? Tau Z1 is 0, yeah. And tau P2 would be 0 as well, right? Tau P1 would be the only one that exists. Okay. All right. So what I would ask you to do, practice in the full practice exam, I'll ask you to do the Bodhi plot of it. I won't do that now. Okay. All right. Enough op amps for now? Dude, time we got left, so we don't have a whole lot, so we got 20 minutes. Bodhi plot? Okay. All right. So let's say we'll do it with an example here. S squared 10s plus 1. I'll not do that. 10s plus 1 S over 100 plus 1 S squared and a negative 20. How's that? All right. So that's my H of S. Now let's say I want to draw that Bodhi plot. So let's go through the steps. And step 1 for me was to figure out where's my poles and zeros. So where are my poles and where are my zeros? How many poles do I have? 3. 3 poles. And what's a pole? Whatever values of S make the denominator 0. So my poles are what?
0, 0, negative.
Yeah, S equal to 0. Yeah, this is weird. I mean, I don't think I would quibble too much with you guys when I look at this. If you told me it was 2, I would probably accept that, and you didn't put the 0 twice. But there's 2 poles, and the reason we, not I, say that I have 2 poles there is because the squared term changes what the graph looks like. All right. By having an S squared, it's going to make the graph fall faster. Okay. All right. How about zeros? What value of S makes the numerator equal to 0? Yeah, negative 1/10 or negative 0.1 or negative 10 to the minus 1. Any one of those. Okay. All right. What would be the corresponding breakpoints? So I'd have basically omega p values and omega z values. What are my breakpoints? Basically, those are the points where the graph changes, right? So what are the points where the graphs change? Yeah, so here it's 0 and 100. And if you told me 0 twice, I'd take that. That's fine. Omega z, what would that be? 10 to the minus 1. All right. Questions about that part? Demetrius, you good with that? Okay. I'm gonna pick on you since you were the one asking me the Bodhi question. All right. So, all right. So we got we got that. So what's the next step for me? Make sure it's in standard form. Is that in standard form? It is. All right. I have tau s plus 1 looks to stuff. What's my k value here? -20. I don't plot the log of -20. What do I plot? I plot the 20 times the log of the magnitude of this thing. What's the magnitude of -20? 20. Okay. All right. So let's draw the graph. All right. Okay. So here's log of omega. Here's 20 log of the magnitude. Like that. Okay. And we're going to make mark off. So here's 0.1. What goes at the origin of this graph? 1. Omega equal to 1. And then the same distance away is 1. Or sorry, 10. What's at the second mark? Mark number 2. 100. Mark number 3, it's 1,000. Mark number 4, it's 10,000. Again, we don't pay too much attention to what's going on down there. Now, what do? At this point, on a test, I most likely would do this. I'd say, okay, well, I want you to graph each individual one for me. All right, so how do I draw? Let's start out with the s squared. How do I draw the s squared poles individually? How would the s squared poles be? Where do they start falling? So if I have a pole, basically I'm flat before the pole, and then I do what? Drop 20 dB per decade. If I have a 0, what do? I'm flat before the 0, and then do what? Rise at 20 dB per decade. All right. So the pole's at 0. Where the heck is that on my scale? -infinity. So they've been falling forever. All right. So we said those are a special case. So I mark out these guys 20, 40, 60, 80 like that. And this will be -20, -40, -60 like that. All right. So how do I deal with those poles at the origin? There's 2 poles at 0. So I would say that they look like this. As I do those 2 decades right there. So 0.1 to 10 is 2 decades. 0.1 to 1 is 1 decade. 1 to 10 is another decade. Each decade, I am dropping from those guys 40 dB per decade. So that would be that, right? This is the 2 poles at omega equal to 0. Okay. What about the pole at omega equal to 100? How would I deal with him? What happens for frequencies below 100? Any ideas? 0. And then once I get to 100, he falls at 20 dB per decade. So 1 decade is 1,000. 2 decades is 10,000. And I should see this guy looks shallower than that guy. The reason he's shallower is because this was 2 poles. This guy was -40 dB every decade. This guy is -20 dB every decade. So he's fallen off shallower. Yeah.
So is it negative? Actually, that would make sense.
Yeah.
Why is it -40?
Because there's 2 of them, basically. So I'm adding the 2 of them together. So the way I think about adding them is basically 2 lines adding together, their slope's going to double. If each one has the same slope, it's going to fall at twice the slope.
That was pulled at 0.
That's right.
But you said it was like that before 0 and then it changed.
Yeah, so where's 0? At omega equal to 0. Where's omega equal to 0? On the log scale, omega equal to 0 is at -infinity. So that's, it's way, way off there. If I got to omega equal to 0, too, because these guys are on the bottom, the magnitude would have been an infinity. Okay. Right. All right. Now I also got a 0 at 0.1 radian per second. All right. So what's that 0 do? It keeps me flat. Then what? Once I get to 0.1, what do I do? Rise up at 20 dB per decade. So by the time I get to here, he's going up at 20 dB per decade. Now this starts to look like some sort of weird 80s video game or Space Invaders, right? There's lasers going everywhere, right? What is this? What do I do to put them all together? I go left to right and add them up. That was step 4. So left to right. So I start all the way out here and I move in that way and I add them up. And my way of doing that was basically say, I'm going to go until I get to the first break point. Up until I get to the first break point, what's the sum of them? The sum of this guy, so the effect of this pole here, and this guy right here is 0. You're right. But I do have this guy who's active always. Okay. So basically, the total graph is, I'm going to draw it thicker. The total graph is this until I get to the first break point. Now, the way I think about this is once I get to that break point, I have 2 poles that are active, and I have 1 0 that's active. So I have a line that's falling at 40 dB per decade. That's coming from the 2 poles. And I have a line that's rising at 20 dB per decade that's coming from the 0. So if 2 lines are going down at negative 20 and 1 line's going up at plus 20, what's the overall slope going to be? So negative 20, minus 20, plus 20. So it's going to be, instead of falling at negative 40, now it's going to fall at negative 20, right? So he's going to be negative 20 from 0.1 to 1 to 10 to 100. I stop at 100 because what happens at 100? I got another break point, right? So I'm going to draw, oh boy. All right. Total's looking like that. Now at that point, I hit another pole. So I hit a pole. So here I'm at negative 40 dB per decade. Then here I'm at negative 20 dB per decade. Then I hit another pole. What's a pole do? It adds another negative 20. So instead of falling at negative 20, now I'm falling at what rate? Negative 40. So when I look at this, is I say, okay, at 10 to the third, a decade away, I better be at negative 60. So I'm falling like that. So the total graph would look something like that. Okay. Yeah.
What would be the type of questions you would ask?
It would be just like this. I would say part A would be step 1. Part B would be step 1B or whatever I called it, right? Right. So what are the poles? What are the breakpoints? Get it in standard form. Draw me the individual parts. Sketch me the sum of those parts. Shift it up or down. Then I probably would ask you one more question, which would be, well, let's say I had an input at 1 radian per second. What would its amplitude be? Right. So I'd ask you to use the graph to tell me an amplitude at a particular frequency. Now I will give you a fuller practice exam that has a couple of those problems. And even for things like the problem that I gave you here, this guy, I would give you, say, sketch the Bodhi plot of that too. All right. So like that. I think you guys should be good with Bodie plots. I can deal with one-off questions from you guys if not. But I feel comfortable putting Bodie plots on the test. All right. I'd rather get those out of the way on this test. All right. Now, I'm going to stop there.